Our speaker today is Julien Tierny, and he will speak about Principal Geodesic Analysis of merge trees.
All right, thanks for the introduction, and hi everyone. It's a pleasure for me to present this work, which is a joint work with Mathieu Bon and Jules Vidal. So our work is motivated by the analysis and visualization of collections of large-scale data sets, such as those that you can find in scientific imaging, like in astrophysics in this example. And such collections are typically obtained by acquisition campaigns or numerical simulations. And the key challenge for the users is to try to make sense out of this collection. So for example, in astrophysics, users typically consider volume data sets such as this one to understand the evolution of a typical structure that they call the cosmic web. However, when they run a data production campaign, users are not confronted to only one data set, but to many, simply because the data can evolve through time, and there may be multiple descriptors of interest, such as matter density or dark matter density, for instance. And also, the data production itself is subject to input parameters, such as specific initial conditions. So this process results overall in a large collection of data sets that we call ensemble. And a key challenge here is to provide analysis tools that will help users visualize and interpret the global trends in the ensemble. Such tools include clustering methods or dimensionality reduction, for instance. However, there are several challenges given the size of the individual data sets in the ensemble. For instance, standard metrics to compare data sets such as the Euclidean distance are not necessarily relevant anymore. And the size of the data sets actually becomes a limitation, even in terms of storage in practice. So to address this, there is this emerging strategy, which consists in representing the ensemble by a collection of topological descriptors, such as persistence diagrams, for instance. And since these descriptors are robust and they encode well the features of interest in the data, this is kind of relevant. Plus, they require storage overhead, which is orders of magnitude smaller than the original data. So the strategy here consists in only storing these descriptors and running the analysis based on these. And this is the core topic of the project Tierny that we run here at Sorbonne University. So regarding the persistence diagram, there is obviously a vast literature which covers both theoretical and computational aspects with fast algorithms for the comparison of diagrams, but also efficient techniques for the computation of more statistical objects, such as barycenters. And however, the persistence diagrams can have limitations, which can be problematic for certain applications. So in particular, it's very easy to come up with two distinct data sets for which the diagram is identical. And in this example, we have two Gaussian mixtures, Fi and Fj, and you have a terrain representation on both sides. And the only difference is that we swapped the positions of the white and the green Gaussian in the two data sets. And it turns out that the two diagrams are identical in this case, although for some applications, it may be desirable to encode this variability. So in our work, we focus on merge trees, which is an alternate representation, which additionally encodes the merge history of the topological features. And in this example, this results in two distinct trees, as the green Gaussian here is immediately connected to the black Gaussian, whereas in the other tree, the green Gaussian is connected to the blue one. All right. So in this work, we'd like to develop statistical tools for the merge trees, which go beyond the simple notion of barycenter, in order to enable an advanced analysis of the variability of the features in an ensemble. And for this, we extend the classical notion of a principal component analysis, PCA, to the Wasserstein metric space of merge trees. So we introduce for this an approach based on for the computation of Principal Geodesic Analysis, or PGA for short. And we formulate this computation as an optimization problem, a constraint optimization problem, for which we introduce an efficient algorithm with an open source implementation. And we also illustrate the interest of our approach into applications. And since our overall approach is based on the Wasserstein distance between merge trees, it trivially extends to persistence diagrams by just modifying a single parameter. So now we'll review a bit the background. The input ensemble is provided as a collection of n scalar fields defined over an object M. And here you have a toy example on the right. The scalar field is simply the elevation of each point of the object, but in the applications, this will be the data to analyze, such as the dark matter density in astrophysics, or pixel values in images and so on. So the object M is modeled as a simplicial complex, as shown here. And now we'll focus on the lower star filtration of the data, which is the sequence of nested subcomplexes obtained by adding the lower star of each vertex by increasing data values. In particular, I will focus on, in the following, on the connected components of the subcomplexes. And basically, a new component will be created when you'll be passing a local minimum of the function, and a component will be destroyed when merging with another one, which was created before. And this is sometimes called the elder rule. And this is what we will visualize in the following animation. So distinct components are created when passing local minima. And when two components merge at the saddle, the youngest of the two dies and will record that change with a bar, as you can see here. And this bar will connect the critical point creating the feature to the one destroying the feature. And if we continue this process, other minima get connected to other saddle points. And here up at the thumb. And eventually we pair by convention here the global minimum with the global maximum. And overall, this gives what is known as the barcode of the connected components of the lower star filtration. And this barcode can be represented in 2D with this notion of a persistence diagram, where each bar, its X coordinate is the data value for the creation of the feature, and the Y coordinates of the extremities corresponds to the creation and destruction of the feature. So the persistence diagram does a good job at capturing the lifespan of the components, but does not capture the actual history of the merges. That is, which component merged with which. And this is where the merge tree comes into play. So the merge tree is a 1D simplicial complex obtained as a quotient space of the mesh by an equivalence relation that says that 2 points, P1 and P2, are equivalent if they share the same data value and if they belong to the same connected component of level set, sublevel set. So like the persistence diagram, the minima of the scalar data will map to the leaves in that tree, and the internal nodes will correspond to saddle points, as shown in this animation. And here you go, all the way to the top, to the root of the tree. So now there's quite a direct relation between the merge tree and the zero-dimensional persistence diagram with the notion of branch decomposition. So by construction, the nodes of the merge tree correspond to the critical points, creating and destroying the components of the sublevel sets. And these are precisely the critical points that are tracked by the zero-dimensional barcode. So you can directly identify in the tree the nodes corresponding to a given bar. And this is what we show here with a color. So each pair of nodes involved a single bar in the persistence diagram. And now that we have this, we can introduce the notion of persistent branch, which is a monotonic path on a tree, which connect two critical points to nodes involved in a given persistence pair. And now the merge tree can be displayed in the plane according to its persistent branches. And for that, we embed each branch of the barcode by putting its extremities at a Y coordinates corresponding to the data values. And we add a horizontal segment to denote the fact that this component merged with this one. So now if you put side by side the persistence diagram and the branch decomposition, the relation is quite obvious. The branch decomposition captures exactly the same persistence pairs, the same bars as the diagram, but the merge tree additionally tracks who destroyed whom with these horizontal segments. So for convenience, we'll consider the branch decomposition tree, or BDT for short, which is just a dual representation of this representation here. So each persistent branch is now represented by a node, and each horizontal segment is represented by an edge here. And here you need to keep in mind that each node of a BDT is a persistence pair. So we augment this BDT with the birth-death values of each node. And this is important because we'll use this later. And in the BDT, you also have the property that the birth-death interval of a branch is included by construction in the birth-death interval of the parent. And we call this the nesting property of BDTs. And this is a direct consequence of the elder rule. So overall, the BDT on the left captures exactly the same information as the diagram, but with additional structure. So in practice, the BDTs may be a little unstable due to a phenomenon called saddle swap, and I will show this now. So at the bottom here, you see a slight variation of the same data set where we just tilted the y-axis a little bit, which results in different data values. And as a consequence, this results in a slightly different branch decomposition, and the history of emergence here is slightly different. So this results in turn in a different BDT, which is not isomorphic, for instance, to the one at the top. So to address this, there is this established strategy that consists in moving up the BDTs, the subtrees, for which the difference in saddle values with their parent is smaller than a given threshold epsilon1. And this is pretty much the effect that we have here. So I'll do it again. And the effect on the BDT is that now these two guys are isomorphic. So this parameter epsilon1 is rather important in practice. We express it as a fraction of the function range between 0 and 1. And if you turn it to 1, all the branches are moved up and get connected to the root of the BDT. And then all the structure of the BDT is collapsed, and the BDT becomes, in a sense, equivalent to the persistence diagram because its initial structure is completely ignored. So really, you need to view this parameter as a control knob that enables users to transition continuously from the input BDT to a BDT with less structure and eventually equivalent to the persistence diagram. So there's also a vast literature regarding merge trees, in particular in the visualization community, where it has been studied over the last 20 years with various applications, including data summarization and segmentation. And recently, there's been this growing interest towards the definition of statistical tools for ensembles of merge trees, including the definition of metrics or approaches for the computation of barycenters, for instance. But overall, there's been little work so far beyond the notion of barycenter. And some works applied the standard PCA to vectorizations of topological descriptors. In contrast, what we'll do today, what I talk about today, is a method to compute the PGA directly on the metric space of these descriptors. And as we'll see later, it results in improved accuracy and interpretability. So specifically, our global strategy is inspired by previous work in optimal transport, which introduced Principal Geodesic Analysis for histograms. But the objects we consider here, the merge trees, are drastically different, so the entire approach needs to be revisited, which is what essentially we do in this work. So now we'll recap the metrics before we move on to the Principal Geodesics. So given two data sets, Fi and Fj, we can compute their persistence diagrams. And these are shown on the right with the white bars for the first data set and the blue ones for the second. We'll consider that the two diagrams have the same number of points, which is something that is easily achieved in practice. And I'll come back to that later if need be. But for the moment, we can safely assume that these two diagrams have the same number of points. Then the L2 Wasserstein distance is given by solving an assignment problem, which tries to match the points of the first diagram to the points of the second, while minimizing overall the mismatches between the points. And the mismatch between the points is expressed here by a function of the Euclidean distance in the birthday space right here. So for this example, here's the solution to this assignment problem with the red arrows. And as we discussed before, the diagrams and its distance fail at capturing the fact that those two Gaussians have swapped between those two data sets because the features in the diagrams are processed independently by the metric, irrespective of the global structure. So this is something that we addressed in a paper a couple of years ago with the notion of Wasserstein distance for merge tree. So given our data sets Fi and Fj, we compute their merge trees and then their BDTs. And from there, we will essentially consider the same expression for the metric, except that this time we will constrain the search space of assignments such that it describes partial isomorphisms between the BDTs. So the change in the expression is minimal. We consider now distance between BDTs, and the only thing that changed is the search space, which is the space of partial rooted isomorphisms. And in this example, you have such an isomorphism shown here, and you have the corresponding minimizer of the assignment problem shown with the sign arrows. And as you can see, since this metric takes into account the structure of the BDT, the sign hill in the first data set is now correctly matched to the sign hill in the second. So at this point, one thing that is important to remember is that a key parameter to that metric is the parameter epsilon1, which we introduced earlier to address saddle swap. And what we said is that this parameter enabled users to progressively discard structure in the BDT such that they eventually become equivalent to the persistence diagram. So now in terms of metric, what it means is that if the parameter epsilon1 is set to 1, basically the BDT is equivalent to persistence diagram, and the search space is not constrained anymore, and the Wasserstein distance between BDTs becomes exactly identical to the Wasserstein distance between persistence diagrams. So then the framework for PGA will be able to support both persistence diagrams and merge tree, depending on the value of that parameter. So once you have computed an optimal assignment between BDTs, a geodesic between them can be obtained by simply interpolating the assignments. So in practice, we represent a geodesic by a vector in high dimension, where the number of dimensions is twice the number of nodes. And this is shown here with this matrix. And this matrix can be interpreted as follows. Each row describes one arrow in the assignment, so one displacement in the 2D bar space. And then you just aggregate them in a big vector. So in blue, you have displacement for the blue points, in black, the displacement for the black points, and so on. So once we have all this, we can introduce the notion of barycenter to compute a representative merge tree. And this is obtained by estimating a minimizer of the fresh energy. And again, this can be computed with an iterative assignment update algorithm, which we introduced 2 years ago. Okay. So now I will start the actual approach that we introduced. So first, I will describe a geometric interpretation of PCA, which will facilitate the transition towards merge trees. So the input to the standard PCA is a set of points in a Euclidean space of dimension D, and PCA defines an orthogonal basis of vectors in the space such that the reconstruction of the input point cloud within the basis is the error is minimized, the reconstruction error is minimized. So PCA can be typically computed in an iterative manner by adjusting a set of orthogonal axes which individually minimize their overall distance to the input point cloud. So this is illustrated here with this point PJ. For instance, we'll first project it to the first axis on the point delta 1. And then delta 1 can be expressed as a translation from the origin of the basis along the first vector, B1. And this translation is weighted by a coefficient alpha 1. Next, we can project PJ on the second axis, and this will yield again a second coefficient alpha 2. And basically, given this new set of coordinates, alpha 1 and alpha 2, you can now estimate your original point PJ by a couple of translations, starting from the barycenter of the point cloud. And if the original point cloud in this example lives in a space that has more than 2 dimensions, you will have a mismatch between your estimation PJ obtained by this couple of translations and the exact point of the input PJ. And this energy at the bottom will precisely measure this mismatch. So typically, the computation of PCA can be viewed as an optimization process where one will optimize the vectors of the basis one after the other to minimize this reconstruction error. So basically, what we'll do in this work is that we'll use the same strategy, but this time in the metric space of merge trees. And for that, we'll go over the basic geometrical tools that are used in PCA, and we'll review their counterparts in the Wasserstein metric space of merge trees. So this is pretty much the list here, and I will go through that. So as we've seen before, a geodesic between 2 BDTs can be represented by a vector with twice the number of coordinates, number of nodes as twice the number of nodes as the number of dimensions. And you have an example here between a barycenter of a set B star and a given BDT epsilon 1. And you have the corresponding geodesic here that is shown with this big vector. So now we can introduce a notion of dot product between geodesics. Basically, given 2 geodesics which share a common origin, we'll first make sure that the 2 geodesics are consistently parameterized. That is, we'll make sure that the entry number I of each geodesic describes the assignment involving the point number I in the common origin epsilon. So basically, we'll sort these vectors to make sure they line up. And once you have this consistent parameterization, you can simply introduce the dot product between geodesics as the standard dot product between their vector representation. And specifically, we'll say that two geodesics are orthogonal if this dot product equals 0. So then, similarly, we can have the notion of collinear geodesic, which happens when you have two geodesics which share the same origin and such that they are equal modulo multiplying factor lambda. And specifically, we'll say that the geodesics are negatively collinear if lambda is smaller than 0. So you have an example of two negatively collinear geodesics. If you take the geodesic going from B star to epsilon 1, and then the one from B star to epsilon 1 prime. And in the birthday space, the second geodesic is opaque and the first one is transparent. Okay, so now that we have the notion of collinearity, we can introduce the notion of geodesic axis. And with this first axis, A1 in blue, and we simply define a geodesic axis as a pair of geodesics which are negatively collinear. And this is represented on the right, where again you have the barycenter, which is the set of points in green, and the axis is represented with these pair of vectors for each point of the barycenter. So here, there, and so on. So for convenience, we'll introduce the notion of direction vector, which is simply the geodesic between the two extremities of the axis. And now that we have this notion of axis, we'll introduce the notion of projection. So given a BDT B, we'll consider as its projection on the axis AI, the BDT B prime on AI, which minimizes its Wasserstein distance to B. And for instance, if this gray point in this figure, its projection on the first axis will be this BDT here, B1. So similarly to the PCA case, the projection of a BDT along an axis can be expressed as a geodesic displacement along this axis, starting at the origin and moving along the axis until we have found the minimizer of the Wasserstein distance. And then we express this minimizer with the linear interpolation along the axis with the coefficient alpha that you see here. Now, this is illustrated on the right, where you have a certain BDT here with the points of this color in gray, and you have its projection here on the geodesic axis, which is shown with these light science spheres. And here, the interpolation coefficient, which is used to encode this projection, is 0.25. All right, so now we can introduce the notion of orthogonal geodesic axis, in particular for this curve A2. And we say that two geodesic axes are orthogonal if their direction vectors are orthogonal. And on the right, in transparent, you have the first axis we've seen earlier, and in opaque, you have the new axis A2, which is orthogonal to the first one. So now we have the tools to define this notion of orthogonal basis. So it's simply a set of geodesic axes with their direction vectors that are all pairwise orthogonal. So once we have this, we can introduce a couple more notions, and then we'll jump to the algorithm. So we can introduce the notion of translated projection, and this will be handy. So basically, we'll use this to translate a certain axis AJ along another AI up to a specific intersection BDT. So this is illustrated here. We have the axis A2, and we are translating it along A1 up to the intersection point B1. And you have exactly the same process that is reflected in the birthday space on the right. So the axis A1 is represented here with this blue segments, and the axis A2 is here, and we translate that axis up to the intersection point to the projection. So now we have pretty much all the tools we need. Given an input BDT, we can reconstruct it by successive projections along translated versions of the axes, such that each projection yields a certain coefficient alpha, in this example, alpha 1 and alpha 2. And this is shown on the right, like I shown before, detailed before. So to recap, given an input data set, Fj, we compute its merge tree and then its BDT. All the computation happens with the BDTs. And then we do this for all the data sets of the ensemble, and we compute the Wasserstein barycenter. And you have it here on the right. And then the BDT basis is defined with a set of geodesic axes having the barycenter for origin. And we have a certain number of axes, 2 in this example. And we'll constrain these axes to be orthogonal. And to estimate our input merge tree, let's say this is this guy, we'll first project our input BDT on the first axis, and that's the sphere B1 over here. And that will yield the tree T1 that you have here. And then we'll translate the axis A2 to the intersection BDT right here. And we'll project our input BDT to that translated axis, yielding our reconstruction noted B hat, and it's going to be T hat for the corresponding tree. And as you may see, we'll have in general a slight mismatch between the input merge tree and the reconstruction by the basis. And the goal of our computational algorithm is precisely to optimize the geodesic axes to minimize this mismatch, which is formalized with this energy. So this energy is really the analog to the energy used for PCA. We have just replaced the L2 distance by the Wasserstein distance, the arithmetic mean by the barycenter, and the translation by what we call projected translations. All right, so I will now describe our algorithm to optimize the energy. So the input is a set of BDTs. There are multiple outputs. The first one is the origin, so the barycenter. The second output is the set of axes, whose number is controlled by the user. And the third output is the set of coordinates of each input BDT in the output basis. All right, so the first step consists of computing the barycenter. And next, we'll proceed to the iterative optimization of each axis, one after the other. So first, we'll initialize the current axis, and I'll detail that after. Next, we'll optimize the axis to decrease the feeding energy. And for that, we'll project all the input BDTs to our current axis. We'll evaluate the energy, and then we'll optimize this energy. And at this stage, we have modified our axes and improved our energy, but the axis has been improved independently of a few constraints, which are at the core definition of the PGA. So now we'll proceed to a constraint enforcement to transform the current solution into a valid solution. So first, we'll enforce the current axis to indeed describe a geodesic. And we'll enforce the fact that the geodesics defining the axis are indeed collinear and in opposite directions. And finally, we'll enforce the fact that the current axis is orthogonal to the previous ones. So these constraints, they can contradict each other. So we iterate this constraint enforcement procedure until the axis does not evolve significantly. And in practice, we simply run a predefined number of iterations, so typically 4. And once the constraints have been satisfied, we iterate the optimization procedure to further improve the current axis. And we continue until the energy does not evolve significantly anymore. And in practice, we stop when the energy has decreased by less than 1% between 2 iterations. And once this is achieved, we lock the current axis and we move on to the next axis until we reach the target number of axes. All right, so to clarify the initialization step, so first, to initialize a given axis, we select the first extremity as the input BDT, which is the furthest away from the previous axes. And if we're dealing with the first one, we just take the one that is the furthest away from the barycenter. So let's say this guy. And then we select as second extremity of the BDT, which is the furthest away from the first extremity, let's say this guy. And now we have our axis initialization, and we'll optimize it now. So the first thing we do is that we sample the geodesic axis uniformly with a target number of samples, and typically 16. And the samples are represented with those blue spheres. And for each input BDT, these are the white spheres, we identify its projection at the axis as the closest sample. And this matching is shown with the dashed blue curves. And the goal now is to update the axis in order to minimize the sum of the squared lengths of this curve. So we'll move this axis to minimize the lengths of this curve somehow. So if we assume that the assignments between a BDT and its projection are constant, it turns out that the feeding energy is convex with regard to the geodesic vectors, and we're providing the paper the analytic expression of the gradient, for which we derive the analytic expression of the vectors which minimize the energy under the current assignments. So at this point, we have optimized our vectors kind of freely, and it is possible that these vectors do not describe a proper geodesic. So this is shown on the right. You have the barycenter in green, and the optimized vector may be this vector here. And in this example, as you can see, these arrows do not describe an optimal assignment in terms of the Wasserstein distance. So basically, we update the optimized geodesic vector to make sure it describes an optimal assignment in the birthday space between the barycenter and the extremity, as shown here. So we go from this dash vectors to the plane vectors. At this point, each geodesic of the axis has been optimized independently, and they may not be collinear. So this is what we enforce now. So we compute the direction vector between the extremities. This is shown in gray. And we update each geodesic to be collinear to that direction vector modulo a certain coefficient here, which is the ratio between the norms of the geodesics. And now the last constraint is to make sure that the optimized axis is orthogonal to the previous axes. And this is achieved with standard Gram-Schmidt projection. And that is pretty much it for the constraint enforcement. As mentioned before, constraint enforcement is iterated a few times. And then we relaunch the axis optimization process again until the energy does not evolve significantly anymore. And once we achieve this state, we lock the current axis and we move on to the next one until we reach the target number of axes. All right, so we'll now move on to some experiments. So first, this is the data sets that we considered, which is available at this address. So we considered 12 ensembles, which were made publicly available in the context of the IEEE SciViz contest. This is a contest which is co-located every year with IEEE Viz, which is the reference venue in data visualization. And each ensemble counted a few dozen members, each with a classification ground truth given by the application. And the merge trees counted between dozens to thousands of branches. And you have all the curation scripts to download the data, to pre-process it, and so on. All of this is available on this GitHub repository. And as you'll see next, this ensemble comes from acquisitions or simulations in various fields, such as astrophysics or mechanics. So first, we report for each ensemble the computation time in seconds for computing the PGA basis for 2 axes. And really, the take-home message of this table is that the computation with 20 cores takes in the order of a few minutes and up to 30 minutes for the largest examples. Now, these plots show the evolution of the energy along the iterations, and on the left, with a PGA for persistence diagram, and on the right, PGA for merge trees. And as we have seen, our optimization procedure first optimizes the axis and then enforces the constraints. And typically, the constraint optimization may increase, in principle, the energy. And this is noticeable, for instance, right here, where you have an increase with a green curve. But then right afterwards, the energy decreases again. And in practice, this didn't impact the rest of the algorithm. This didn't prevent it to lower the energy afterwards. So in this curve, you can clearly see some discontinuities over here. And actually, they correspond to the end of the optimization of one axis when we switch to the optimization of a second axis. And all of a sudden, the energy decreases as soon as you add more axes to the basis. And one thing that is also interesting here is the projected variance, which is shown in the inset here. And one thing that is interesting to see is that the projected variance of the axis does indeed decrease as we add more axes. And this is what we see in the inset since all these points are below the diagonal. So we had more variance with the first axis and less with the second. And this shows somehow that the algorithm selected the most informative axis first. Right, so I'll now move on to a few applications of our work to data analysis. So the first application that we consider is data reduction, where we basically use the PGA to compress the descriptors. And the idea is simply to store to disk the basis, so the barycenter and the axis, and then store to disk for each merge tree its coordinates in the basis. And then we'd like to evaluate if we can still perform the same analysis tasks with the compressed merge trees, which we obtain from the coordinates. So first we try this with feature tracking, where we consider a time-varying data set with 3 time steps. And for each time step, we compute its merge tree. And then we try to track through times the most persistent features by considering the optimal assignments between consecutive time steps. And what we can see in this example is that the main maxima of this data sets are correctly tracked through time. Now we'll compress the ensemble with our PGA basis and use the reconstructed trees to achieve the same task. And in this example, for a compression factor of about 5, we achieve exactly the same tracking of features. We tested this for topological clustering as well. And we took this ensemble from astrophysics, which has 4 ground truth classes. And you have 1 example per class here. We computed the merge tree of each data set, and we performed the clustering on the metric space of merge trees. And for this ensemble, the clustering reports the exact classification, which is the one from the ground truth. So the question is now, can we use our compressed merge trees, compressed by PGA, to do the same task? And here you can see the trees decompressed from the basis, and here the compression factor was about 19, and the clustering obtained with the compressed trees was identical to the clustering obtained with the input trees. So that example confirms the practical usability of the merge trees compressed by PGA. So the next application we consider is dimensionality reduction. And here the idea is again very simple. We use only 2 axes, and we represent each merge tree as a point in 2D based on its coordinate in the PGA basis. And we compare this to various strategies. So first we do a standard PCA on the actual data values. And next we consider the Wasserstein distance matrix between the merge trees. And we feed that distance matrix to MDS and TSNE in these columns. And finally, we consider a vectorization of the input merge trees inspired by previous work. So specifically, we vectorize each merge tree with respect to the barycenter of the set. So the ith entry of each vector corresponds to the branch that maps to the ith branch of the barycenter. And once we have this vectorization, we run the standard PCA, and this is what you have in this column, MT-VEC. And we evaluate the quality with 2 sets of indicators. We have the indicator sim, which is equal to 1 when the matrix has been exactly preserved. And you have the indicators NMI and ARI, which are equal to 1 when the clustering computed in 2D is identical to the ground truth. And in this visualization, the ground truth classification is reported with the color from red to pink. And you have a comparison for 2 ensembles from our database. And the outcome here is that the vectorization approach tends to provide the worst scores, and MDS tends to do the best job at preserving the metric, and TSNE tends to do the best job at preserving the clusters. And MT-PGA tends to provide a trade-off between MDS and TSNE. This is confirmed when we look at the averages of these indicators over all the ensembles that we had. So basically, MT-PGA provides a trade-off between those 2 behaviors of MDS and TSNE. So the fact that we compute the PGA directly on the metric space is also helpful in terms of interpretability, especially for visualization. So this is an ensemble of a hurricane simulation with 12 data sets in 3 classes. At the bottom, you have 1 example of data set per class, along with the corresponding persistence diagram. Now, right above, you have the persistence diagrams reconstructed by PGA. And you can see that the diagrams are visually similar with the most persistent features which nearly coincide. And here is the planar view of the ensemble generated by PGA. So each sphere represents an input diagram, and the color encodes the ground truth classification. And you can see that the clusters are well separated in this 2D layout. And an interesting aspect of our approach is that we can reconstruct a persistence diagram for any coordinate in the PGA basis. So in particular, what we'll do next is that we'll generate a persistence diagram for each of the vertices of this background grid. From there, we'll compute the distance matrix between all of these generated persistence diagram. And finally, we'll feed that distance matrix to MDS to project the grid, but this time in 3D. And this is what we've done here, and this is the result, which shows essentially the same information as the planar view, but the 3D aspect conveys some information about the distortion induced by the planar view. So basically, it will get curved when the points were actually kind of closer in the metric space. Now that we have this 2D parameterization, we can investigate the variability within the ensemble at a feature level. So for this, we'll have a look at the barycenter. And for each ith point in the barycenter, we'll consider the points in the diagrams where it matches by optimal assignment, and we'll measure the correlation between the persistence of this feature and the coordinates in the basis. And that results in what we call the persistent correlation view, where we report the most persistent features of the barycenter. And the way to interpret this is that this blue feature here, which corresponds to this point, is the eye of the hurricane that you can see at the bottom, and it will be very persistent if you move in the 2D layout along this direction. So in short, the persistence of the eye of the hurricane will be very high if you go towards the left of the 2D layout, which corresponds to the first two clusters, which are phases of the data where the hurricane hasn't touched ground yet, and after the landing, the persistence of the eye decreases. From this correlation view, you can also see those three features at the bottom. They will have their strongest persistence in the bottom right quadrant of the 2D layout, which is kind of in between those two clusters, the last two clusters. And these features correspond to the areas of strong wind on the corners of the domain here. You have a similar example for an earthquake simulation, and you have a seismic wave that travels through time. You have three ground truth classes for the ensemble, and we report one data set per class. Again, you have the corresponding merge tree, the reconstructed trees by PGA. And you can also have the 2D layout and have a look at the 3D surface to have a better sense of the distortion. And again, we can plot the persistence correlation view to track the variability of each feature. So since we can reconstruct arbitrary locations in the basis, we can even provide a user-defined curve here in purple in the 2D layout, and we can reconstruct the corresponding trees. And this generates sorts of continuous navigations in the space of merge trees between the clusters. Okay, so we can try all this. This framework is integrated in the development version of TTK, the topology toolkit. And to try this out, you can go to the TTK example website, which includes dozens of examples of analysis pipelines with TTK. And for each example, you have a screenshot, a quick description, a command line to reproduce the screenshot, and a Python snippet. And if you want to reproduce the examples we've just seen before, you just need to go to that web page in particular. So to conclude, we have presented a computational framework for the principal geodesic analysis in the Wasserstein metric space of persistence diagrams and merge trees. A unique aspect of this work is that we run the entire computation in the metric space directly. And this resulted in improved accuracy and interpretability. And we have shown the utility of this framework in two applications, compression and dimensionality reduction. The paper that describes this work has been certified replicable by the Replicability Stamp Initiative, so you can download the exact data and code that we used to reproduce our results. And obvious directions for future work include the consideration of more advanced descriptors, such as the rip graph, for instance, and also the consideration of more advanced analysis than PGA, but still in the metric space of merge trees. All right, and this concludes my talk. Thanks for your attention, and I'd be happy to take questions now.
Thank you very much. Let's please all unmute ourselves so that we can clap together for our speaker. Very good. Do we have any questions? Maybe while people are thinking what their questions are, I can ask one myself. I was wondering about the role of this parameter. I forgot what it was called, maybe epsilon, where you said you can go between merge tree and persistence diagram.
Absolutely. Let me try to go back here. I think it's in these slides right here, right?
Yes, exactly.
Yes.
So, for example, when you were explaining this PGA approach, is there the parameter epsilon fixed, or?
So basically, when we do the PGA for persistence diagram, this parameter is fixed to 1. So that means that we move all the branches up. So then you end up working with the persistence diagram. And then when we use the merge trees, we set this parameter to a fixed value, which is the value that was recommended basically in the original paper.
Okay, cool, thank you.
But this parameter in practice has some importance, especially with regard to the practical stability of the metric.
Yeah, I was wondering how to choose this parameter, but I guess that's described in the other paper.
But in a sense, if you know that you have a noise that is smaller than this threshold, you can basically use this threshold, epsilon1.
Okay, thanks. And in the meantime, we have 2 questions in the chat. Can this method be used for manifold learning? And I guess it's a follow-up question. Do you have any idea for predicting curvature?
Wow. So manifold learning, I guess this method is geometric in a sense. So basically we have all those merge trees, and we're trying to recover a parameterization of that space, but really we don't tell anything about the actual topology of the space, for instance. For that, you would need to consider, for instance, a Reeves complex or something. So what we're looking at is really trying to find a parameterization that is kind of faithful to the metric. So if you have some assumptions regarding the dimensionality of the manifold of your merge trees, maybe you can use that as the maximum number of dimensions that you want in the basis. That's one thing. Then regarding the curvature, that's a really good question. So, I mean, we started to play a bit with it in terms of visualization, and this is shown in this slide, where basically we have this 2D layout that is shown in 3D to better respect. So we designed this visualization in 3D to be more faithful to the metric. And what it shows is that, for instance, if you have a valley in the surface, that means that 2 points that were far in the 2D layout are actually closer than this in the metric space. So now, if you have some assumptions about the dimensionality of your space, and you know that it's 2D, well, that means that it's curved, but maybe it's just that the space has more intrinsic dimensions. So yeah, in short, you can have a sense of the curvature if you know the intrinsic dimension of that manifold, I guess.
Oh, thank you. Okay, more questions.
I have a couple of questions.
Yes.
Go ahead.
Can I go? Okay. The first one is, if I understood correctly, the idea behind this principal component analysis comes from the fact that by pairing the persistent pairs up to adding like persistent pairs on the diagonal, at least locally, you are on some copies of the Euclidean plane, one for each persistent pair.
Absolutely, absolutely.
But
yes,
the space that you get is constrained in such a way that basically you need to do all the steps about the geodesics enforcement, orthogonality.
Absolutely.
But do you have an idea of like how badly behaved that space? I believe like it's not convex and or other things. And so the question is also, have you tried like changing the parameterization of this space to get something, for instance, which is convex, which would simplify things much more?
That's a good question and a natural question. So the short answer is that taken as is, the energy that we try to minimize is not convex at all, and this is very easy to argue. So obviously the optimization is in principle difficult, but what we've seen in practice is that that happened to work well. So we run many experiments, and we didn't run into an issue where the solver was diverging. One thing that may be helpful here with remark to the second part of your question, how to convexify this thing somehow. So actually, if you look at the original paper by Tierny and co-authors in optimal transport, where they had the same overall strategy, but for histograms, and there they used all the machinery from entropic transport, where things tend to be, the energies tend to be much more convex, and still they had the same issue of trying to optimizing something that was not convex. So that's definitely one of the issues of this approach.
I believe that my question was slightly different.
Okay.
And that I was not like, I didn't mean the convexity of the functional that you are optimizing, but the convexity of the space, which is exactly what happened for the Wasserstein case or histograms or distribution on the real line. What makes that method work is because it's inside a convex space, so you can do optimization with using the fact that if you take segments within the space of histograms or distributions on the real line, is going to be still an histogram, and that is going to be a geodesic, the segment. Yeah, you see the point I'm making? Because if you could turn the space of your space of merge tree is into something like that, then you could use also like the regression they define for Wasserstein spaces of distribution and a lot of other tools that they have there.
Yeah, absolutely. Yeah, I don't have a clear answer to that former question then. No.
And if I may, I'll last a very quick question. Have you tried to compare the Wasserstein metric with the LP metric for merge trees?
So which metric are you talking about specifically?
I think it's a paper that came out maybe 1.5 years ago, which is basically, yeah, it's the universal distance for merge trees when you use some P norm for functions. I believe that at least in spirit is not super far from your Wasserstein distance.
Okay.
But it's but yeah, it's different. But and I don't know, it's quite complicated, and there's not an algorithm to compute it in complicated scenarios. So I was wondering.
Oh, okay. So the short answer was no.
Okay.
The thing also. One of the reasons why we continue down that path of that Wasserstein metric is because with this optimization framework, we need to compute thousands and thousands of distances. Okay. When we project a BDT to an axis, basically we sample it, and for each BDT we compute as many distances as samples, and we do this for everybody and for every axis. So yeah, we need to have something that's computable for sure.
Okay, thank you.
Yeah, you're welcome.
Thank you. Who wants to ask the next question? I have actually another one myself. You in the very beginning showed this astrophysics example. Do you there have data with periodic boundary conditions?
Not from this application, but we've been running in other applications, especially in chemistry, when they're trying to model crystals and things like that, where they have periodic conditions. We haven't tried this data for this specific work, but this is something we've been running into sometimes. Yeah.
Yeah, because I'm myself actually working on extending the merge tree to a periodic setting. And I was wondering if then this periodic merge tree could also be used for this framework that you're using. But yeah, maybe we can chat about this another time.
Oh,
it's overly specific.
That'd be lovely. Yeah, please.
Great. Okay, any more questions for the recorded part? Okay, then maybe I will end the recording here, and then people can still ask questions later. Thank you very much again.
Thank you.